Hey folks, welcome back. Here's the beginning of our new way of doing things for a while. Hope everybody's okay, uh, healthy and safe. And let's go ahead and see how this works. I'm starting on chapter 11, and that chapter is on momentum. It's a new quantity as far as we're concerned. And it's really important. It turns out to be another conserved quantity in the same way that energy is. So it turns out to be really useful. I'm going to start up here in the upper left-hand corner. So chapter 11, momentum and impulse. Impulse is closely related to momentum. And to start off, I'm going to tell you that what I've told you before about Newton's laws isn't exactly right. Okay, Newton, he didn't write the sum of the forces is equal to mass times acceleration. Not exactly. Here's what he actually wrote. The sum of the forces acting on an object is equal to its change in something he called the quantity of motion. Okay, so the symbol lowercase p is used. It's a vector. Okay, it's got a direction associated with it. And he considered the quantity of motion, any change in that signified that there was a net force acting on an object. The way he defined the quantity of motion was, we now call it momentum, by the way. P is a vector quantity and it's equal to the mass of the object times the velocity of the object. So the velocity is a vector quantity. So if you multiply that by mass, that's what he considered to be the quantity of an object's motion. You think about it, what's the important aspects of the motion of an object? Well, it's not only how fast it's going and in what direction, but also how much material is there. So the mass and the velocity are involved in this. Now, it turns out that that is not exactly the same thing as MA. And here's how you know. If you go ahead and sum the forces and set them equal to the change in mass times velocity of an object with respect to time, dp dt, then you have to use the chain rule because you've got two different quantities. So you've got the first quantity times the derivative of the second with respect to time, plus the second quantity times the derivative of the first with respect to time. So if you use the product rule, you end up with this first quantity, m times dv dt, that's the same thing as ma, so that part is what you would expect. But now, what if the what if the mass of the object is changing with time? Everything we've dealt with so far didn't have a change in mass with a change in time, but think about a rocket. As a rocket goes up, it's throwing material out the back end of it at a super high speed, and it's changing mass very, very quickly. So you couldn't use this equation on a rocket, and we're going to derive the rocket equation later using the second term in the second law of motion, which is pretty interesting. I really like the rocket equation. So in any case, if the mass is constant, then yeah, it does reduce to sum of the forces is equal to mass times acceleration. But if the mass of the object does change with time, then you have to keep this second term involved. Okay, now, so if we start with Newton's original way of writing the second law, the force on an object is equal to the time rate of change of its momentum, then let's see, we multiply both sides of the equation by that small increment in time dt. So we get f dt on one side and dp on the other, the change, the infinitesimal change in momentum. Now, if we integrate both sides of this, then we'll have the integral with respect to time of the force over an interval t initial to t final. That's going to be equal to the integral dp from p initial to p final, where this p corresponds with the momentum of the object at time t initial. This p corresponds with the momentum of the object at this time t final. And so this is just going to be delta p, p final minus p initial. So the change in the momentum of an object is equal to the integral of the force with respect to time of that object. And that change in momentum is also given the symbol capital J, and capital J is the impulse of the system. Okay, so impulse is the change in the momentum of an object. So in other words, if an object is pushed for a certain length of time, then it has received an impulse and its momentum will change. Okay, if I come up and push you with 100 newtons of force for 10 seconds, I've applied a force through time on you. So 100 newtons times 10 seconds, 100 times 10 would be 1,000, and the units would be Newton seconds. And that's one way to express impulse units. There's another way too, because momentum is mass times velocity, so you can express it as kilograms meters per second as well. A kilogram meter per second is the same thing as a Newton times a second. So you can, if you break a Newton down, you'll get kilograms meters per second if you multiply newtons by seconds. So you can use either units for impulse and momentum. All right, so the impulse equation is here. The change in the momentum of an object is equal to the integral of the force with respect to time over that time interval. And by the way, this is really just the integral version of Newton's second law, right? Newton's second law is a differential equation. Here's the integral version of the same equation. When would you want to use this? Well, if you want to find the change in momentum of an object and you know the force is acting on it, you can use that to do so. Also, since the change in momentum is equal to the integral of the force with respect to time, hey, an integral shows the area underneath the function, right? So here, if you graph function on the vertical axis and time on the horizontal, the area underneath the curve, so now this represents a changing force with respect to time acting on an object. The area underneath that is going to be impulse, or the change in the momentum of the object. Okay, so now if we take an isolated system where there's no outside forces acting on an object, then if we sum the forces acting on the object, they're equal to 0, right? If it's an isolated system with no outside forces. And that 0 is equal to the time rate of change of the momentum. So if the derivative of the momentum is equal to 0, that means necessarily that the momentum itself is constant. So in an isolated system, if the momentum is constant, then the initial momentum is equal to the final momentum. And now this is conservation of momentum. So this is how you arrive at the law of conservation of momentum, one of the fundamental conservation laws in nature. Okay, and I'm going to use the conservation of momentum to do a simple problem that I've got up here. Okay, now here's the example. You've got a boxcar that's moving with a speed of 10 meters per second initially, and it runs into another boxcar that's also moving to the right, but it's moving at only 5 meters per second, so there's going to be a collision. The momentum of the first car is 10 to the 4th kilograms. Momentum of the second car is 4 times as great. It's a much more massive car. Okay, so here they crash, and now they're locked together, and they're moving off as a single object now. 2 objects locked together. And now I'm going to use conservation of momentum to solve this problem. The initial momentum of the system is going to be the momentum of these 2 cars before they collide. So what you have to do is multiply their masses times their velocities and add the 2 terms together to get the total momentum of the 2-car system. So let's see, 10 to the 4th kilograms times 10 meters per second gives you 10 to the 5th kilograms meters per second for the momentum of the first car before the collision, plus the momentum of the second car before collision, which is going to be 4 times 10 to the 4th kilograms times 5 meters per second, and that gives you 2 times 10 to the 5th kilograms meters per second. So if you add these 2 together, 10 to the fifth plus 2 times 10 to the fifth, you get 3 times 10 to the fifth kilograms meters per second. So that's the total momentum that the two-car system has. And now if you set that equal to the final momentum after the collision, you can solve for the final velocity of these two after they lock together. Okay, so the final velocity is going to be equal to the total mass of the two cars together, which is going to be 1 times 10 to the fourth kilograms plus 4 times 10 to the fourth kilograms, which is 5 times 10 to the fourth kilograms. Now if you multiply that by the unknown final velocity, that will be the momentum of the system after the collision. But since there's no outside forces acting, then you can set that equal to the initial momentum that we've just calculated to be 3 times 10 to the fifth kilograms meters per second. If you divide through by 5 times 10 to the fourth kilograms to isolate the final velocity, you get that the final velocity is 3 times 10 to the fifth meters per second divided by 5 times 10 to the fourth, and you end up with 6 meters per second. So after the collision, the less massive car has slowed down from 10 meters per second to 6 meters per second. But the slower car, which was originally only going 5 meters per second, is now sped up by 1 meter per second to 6 meters per second. Now, does it make sense that this would be the final velocity? It makes all kinds of sense, okay? The final speed has to be something less than 10 meters per second, okay, but something greater than 5 meters per second, right? It has to be going faster than the slower thing and slower than the fastest thing. Okay, the slow thing's going to slow down the fast thing's going to speed up the slow thing. Now, why wouldn't it be exactly halfway in between? Well, it would be if the masses were identical, right? But it turns out that the more massive thing was less affected by the collision than the less massive thing. That makes sense, right? And by how much? Well, it turns out that the more massive thing, which was 4 times more massive, was affected only 1/4 as much by the change, showing up as a change in speed. So that makes all kinds of sense. And here we've used conservation of momentum to solve this problem. All right, I'm going to stop at this point and refill the board. Okay, now picking back up, I've erased the board. Well, I didn't erase the bottom part of this board. That's the last problem that I did. And what I went ahead and what I did was I found the velocity of the two cars after they hit and stick together. Okay, now the question is kinetic energy lost? There's no change in gravitational potential energy in this case, right? Because these two cars are on a level surface. Neither one of them is changing their vertical height at all. So no change in gravitational potential. We haven't talked about spring potential here at all. So that doesn't come into play here. Is there a change in the kinetic energy? Is there a change in the overall mechanical energy of the system? Well, we can find that out. And I got that started over here. So was kinetic energy conserved in this collision? In other words, was mechanical energy conserved in the collision? Because there's no change in the potential. And remember, mechanical energy is a combination of kinetic plus potential. So let's see if we can figure this out. What we need to do is find the initial kinetic energy before the collision and the final kinetic energy after. We've got everything we need to do that. So the initial kinetic is going to be the kinetic of the first object before collision plus the kinetic energy of the second object before collision. If I plug in the values, which I've done here, so you can look at that, when you want to. I'm not going to go through all the numbers right now, but the initial kinetic energy turns out to be 10 to the 6 joules, a million joules of kinetic energy that the two cars have before they collide. Now compare that to the final kinetic energy. The final kinetic energy is going to be 1/2 times the mass of the two objects together, because they're traveling now as a single object, times their final combined speed, which is 6 meters per second squared. And if you do that, you get 9 times 10 to the fifth, or 900,000 joules. We started with 1,000,000 joules before the collision. We ended up with only 900,000 joules after the collision. So that tells you that there's a loss in kinetic energy of 100,000 joules. So energy was lost. Where did it go? 100,000 joules of kinetic energy was lost in the collision due to work done in deforming the objects. Thing 1 applies a force through a distance on thing 2. Thing 2 does the same thing back on thing 1. So work was done, and that shows up as a loss of the mechanical energy of the system. In this case, it's just the kinetic energy, which is lost. So it turns out that that's a certain class of collisions. We separate collisions into several different types. The first type is an inelastic collision. If something is inelastic, when a force is applied to it, its geometry changes, okay, and it stays changed. An example of an inelastic collision would be, say, 2 billiard balls hitting each other, okay? If you could look at them with a microscope in, slow motion film, you could see that they actually deform a little bit during the collision. The collision takes a certain amount of time, and then they part. So they leave with the same geometry that they met each other, and so whatever energy was used during the compression of the objects, it's regained as they spring apart. Okay, so there's no net work done on the objects due to deformation. So that means that the momentum is conserved, but also the kinetic energy. For an inelastic collision, like two cars hitting each other and sticking, there is work done by the two objects, and so there's a loss in kinetic energy because work is done in deforming the objects. Disregard this right here. Okay, so in an elastic collision, it's the other way around, like billiard balls. Kinetic energy is conserved. So what we found was that the collision of the rail cars was an inelastic collision. We were able to find out how much energy was lost or used in the deformation of the objects. Okay, in the case of an elastic collision, not only momentum is conserved, but also the kinetic energy, because there's no work done, net work done on the objects on each other during the collision. And here I'm going to model an elastic collision where no damage is done to the object. So I've got two blocks that are both moving to the right. The smaller block is a 1 kilogram block moving at 2 meters per second. The larger block is moving more slowly at 1 meter per second, also to the right. It's a 3 kilogram block, so they're going to hit each other. And so here's before the collision, after the collision. What we want to do is find out what the final speed of these two objects are. They parted, so now there's going to be two kinetic energy terms, right? Over here, for this problem, there was only one kinetic energy term because the two things basically became one after the collision. So we're going to have to find both of these velocities. Now, so we've got these two criteria that have to be met. The initial momentum of the system is going to be the momentum of both objects. So let's see, the momentum of the 1 kilogram block is going to be its mass times its velocity. So 1 times 2, that 2 represents the momentum of the first object before the collision, plus the momentum of the 3 kilogram block moving at 1 meter per second. 3 times 1 is 3, so 2 plus 3 is equal to 5 units of momentum. I didn't put them in there because I was running out of space, but the units are kilograms meters per second, okay? Now, the momentum of the final system after the collision, well, it's going to be the mass of the first block, 1 kilogram, times its unknown speed, which I'm calling VA. So there it is, plus the momentum of the second object, which is going to be the mass of it, 3 kilograms, times its unknown velocity, VB. So the final momentum of the system is going to be equal to VA plus 3VB. So if you set the initial equal to the final, you get this equation in the box here. 5 units of momentum before the collision has got to be equal to VA plus 3VB. So we've got one equation with two unknowns, so we can't solve yet. So what do we need to do? We need to go to the second criteria and set the initial kinetic energy equal to the final. So the initial kinetic energy, use the kinetic energy equation on each object and add them together. 1/2 times the mass of 1 kilogram times the velocity of 2 meters per second squared, plus 1/2 times the mass of the second object times its initial velocity squared. Okay, and what you get is 3.5 units of energy, 3.5 joules of kinetic energy that the two objects have before they collide. Well, after they collide, if it's an elastic collision, then the kinetic energy has to be the same, but we don't know what the velocities are after the collision, so it's going to be 1/2 times the mass, 1 kilogram times VA squared, plus 1/2 times the mass of the other object, 3 kilograms, so 3/2 VB squared. So if you set 3.5 equal to 1/2 VA squared plus 3/2 VB squared, and then you multiply by 2 to get rid of the fraction, then 3.5 times 2 gives you 7 is equal to just VA squared plus 3 VB squared. So now this equation and this equation we got from meeting these two criteria: conservation of momentum, conservation of kinetic energy. Two equations with two unknowns. Now we can solve. So a good technique here: VA is equal to 5 minus 3 VB. What I did was I solved for VA in this equation right here, and now I'm going to square it. I'm going to square both sides of this equation because the second equation has VA squared in it, not just VA. So if I square this equation, VA is equal to 5 minus 3 VB, then I get VA squared is equal to 25 minus 30 VB plus 9 VB squared. Now if I take this way of representing VA squared and plug it in right here into the second equation, then I'll have an equation in terms of only VB. So this equation then becomes, if I substitute in this way of writing VA squared, I get 7 is equal to 25 minus 30 VB plus 12 VB squared. Okay, I added the 9 VB squared to the 3 VB squared here to get 12 VB squared. Okay, now if I subtract 7 from both sides, I get 12 VB squared minus 30 VB squared plus 18 is equal to 0. So I've got the quadratic form. And now if I divide through by 6, I can simplify it a little bit further. I get this, and then I was able, because these coefficients are so small, I was able to factor this into two binomials by inspection, and so I get 2 V3 minus 3 quantity times VB minus 1 quantity is equal to 0. So now that's only going to be possible if this factor is equal to 0, or if this factor is equal to 0, or both. So if you solve them like that, if you set this equal to 0 and solve for VB, you get VB is equal to 3/2 meters per second, or if you set this factor equal to 0, then you get VB is equal to 1 meter per second. Okay, now the way to validate your work, you know, there were quite a few steps in this problem. It's all simple algebra, but quite a few steps. What you need to do is look and see if one of these two possible answers is the same velocity as the object had initially, and it is. Here we've got one of the answers being 1 meter per second. The initial velocity was 1 meter per second. So the other, that lends validity that this must be the actual speed of the second block after the collision. So it's sped up from 1 meter per second to 3/2 meters per second to the right. And if you plug this value in to this equation down here, you can solve for VA, and VA turns out to be 1/2 meter per second. So the 1 kilogram block was initially going 2 meters per second. Now it's only moving to the right at 1/2 meter per second. Now one way to interpret this is, think about it. What's happened here is that momentum and kinetic energy were conserved in the collision. Think about it if block A missed block B and just went by without touching. Well, in that case, momentum and kinetic energy would be conserved as well. So you can think about it as one of these is a hit and one of them is a miss. That's an example of solving a problem that involves no loss of energy during the collision. We've done both types, an inelastic collision and an elastic collision now. Okay, I'm going to stop.